Hi there, and welcome to the third chapter of this course on resistivity tools. In this section, we will cover the applications of these tools and what they are really measuring. We will start by distinguishing between induction tools and lateral logs. And finally, we will cover micro resistivity tools. Let's jump in. By the end of this module, you will be able to understand the different types of resistivity tools, select appropriate tools based on the logging conditions, also to understand the physics of the measurements, and finally, evaluate the resistivity tools measurements resolution by understanding concepts like depth of investigation and vertical resolution. Let's get started. In the field of wireline logging, there are several types of resistivity tools. The basic types are induction tools, Laterologs, and micro resistivity tools. Additionally, there are more advanced services like resistivity imagers, but this course is focused on the basic types. The primary objective of running an induction tool or a lateral log is to determine a value for true resistivity, RT, of a formation. That is, resistivity of the uninundated zone. And the primary objective of logging a micro resistivity tool is to estimate the depth of invasion and to determine a value for flushed zone resistivity, RXO. But how to determine in which case to use a lateral log or an induction tool? As a rule of thumb, if the ratio between the resistivity of the mud filtrate, RMF, and the formation water resistivity, RW, is less than or equal to 2.5, we should use a lateral log. If the ratio is greater than 2.5, induction tools are preferred. Induction tools are best suited for non-conductive and low conductivity boreholes, such as those drilled with air, oil-based mud, or fresh water-based mud. On the other hand, in boreholes with saltwater-based drilling fluids, the borehole effect is too significant for induction tools to provide an accurate measurements of formation resistivity. In such cases, using lateral log tool is more effective. Because lateral logs provide best results where there is low contrast between the salinity of the mud filtrate and the formation water. Lastly, micro resistivity tools provide best results in conductive borehole fluids like saltwater-based mud or in fresh water-based mud. Let's learn about the physics behind how resistivity tools work. Since the principles differ between induction, lateral logs, and micro resistivity tools, we will cover each one separately. First, let's start with induction tools. Induction tools use a basic setup of a transmitter coil and several receiver coils. For simplicity, we'll draw only one receiver coil in this example. When a current flows through the transmitter coil, the X shown in green, it creates a primary magnetic field. This magnetic field induces a current or primary ground loop in the surrounding rock formation. This primary ground loop generates a secondary magnetic field, which then induces a voltage in the receiver coil, Rx, shown in red. This voltage, known as the R signal, is important because it is related to the formation's conductivity, and by knowing the formation's conductivity, we can calculate its resistivity, which is just the inverse. However, there's also an unwanted voltage caused by the direct coupling between the transmitter and receiver coils, known as mutual signal, which needs to be corrected. In formations with very low resistivity, less than 3 ohm meters, another voltage called the X signal appears into a secondary ground loop. This also needs to be corrected. In summary, the principle of operation of an induction tool is to apply an alternating current to a coil, generating a magnetic field, which will induce a current into the formation. Then, the receiver, which is another coil, will measure a voltage that contains 3 main components. The R signal, which captures the resistivity of the formation, mutual signal interaction between the transmitter and receiver coil, and the X signal, affected by the conductivity of the very low resistivity formations and borehole fluids. Now let's study another type of resistivity tool, Laterologs. The purpose of using a lateral log is to accurately determine the true resistivity of underground formations, RT. This tool works by injecting an electrical current into the formation using electrodes. Then, the current travels through the formation and it returns to the tool's receivers. By understanding the geometry of the current flow, we can apply Ohm's law to calculate the resistivity of the formation. Remember that we want to determine resistivity values from different distances from the borehole, one for deep measurements and one for shallow measurements. Well, for this to happen, we need to find a way to make the injected current to flow in a specific way. Here we can see a diagram of a lateral log. As you can see, it has several metallic electrodes positioned along the tool string and are electrically isolated from one another. The current comes out from the transmitter, Tx, here shown in green. This current is called survey current, and we have one for shallow gratings and one for deep gratings. Then this current travels through the formation and returns to the tools on a different electrode called current return, in this graph shown in red as Rx. But once the injected current goes out of the tool, the natural tendency is to follow the path of least resistance, which it unfortunately does not cover all the formation, but the borehole and tool housing. To overcome this issue, other electrodes called guard electrodes are employed to emit a focus current shown in yellow. Please note that the survey current is the one of main interest, since this will provide information for resistivity. There will be, for sure, other electrodes depending on the service company that manufactures each lateral log, but this is the general principle of operation of all of them. Now we move to talk about micro resistivity tools. Keep in mind that the reason behind logging a micro resistivity tool is to estimate the depth of invasion and to determine a value for the flushed zone resistivity, RXO. Considering that the flushed zone extends several inches from the borehole wall, a measurement of its resistivity is best achieved by a pad-mounted electrode device, such as the micro resistivity tool. The way this tool works is basically injecting a current using an electrode that is mounted into a pad. The idea behind using a pad device is to keep contact with the borehole wall and create the conditions for this injected current to travel through the flushed zone. But again, injecting a current usually implies that the current will flow the path of least resistance and will travel through the borehole or the tool housing. Therefore, to make the injected current, called survey current, flow through the flushed zone, another current called focus current is injected. Something similar happens in this case of a lateral log, but keep in mind that whenever we talk about micro resistivity tools, our main focus is the flushed zone and the shallow measurements. In this section, we'll discuss the resolution of the measurements for resistivity tools. If you read the dataset for an induction, lateral log, or micro resistivity tool, you will find two key concepts: depth of investigation and vertical resolution. Depth of investigation is defined as the distance from the tool beyond which 50% of the measured signal is originated. For example, consider a tool with a 90-inch depth of investigation. Half of the tool's measured signal originates from volume beyond a 90-inch radius of the tool, while the remaining half originates from the volume within 90 inches radius of the tool. Another key concept, vertical resolution, which is defined as the minimum bed thickness that can be observed on a tool's response. For instance, if a tool with a 2 feet vertical resolution is capable of responding of a formation of 2 feet thick, However, this does not necessarily mean that the tool is capable of an accurate measurement in such a thin formations. In very thin formations, a large percentage of the tool's response depends on the properties of adjacent formations.